All right, so before we kind of dive into this section, note that I probably will not go into every part of this section. So kind of quick thumbs up, who has at least started within section 23? And it's okay if you haven't yet. Okay, and a couple of thumbs up, cool. All right, so if you are in section 23, like I mentioned before, what's it called, in on Slack, is go through section 23. I am going to strongly suggest skipping over MLE. You know, you're welcome to go through it, but it's not needed. To be quite honest, it's very technical. It's kind of tough to really understand. And so I want to go into more detail of what's going on there. So the good news is that's also not part of the project, really. We're going to see it again in module 4, so the next module coming up with logistic regression. So again, my suggestion right now is if you're feeling kind of pressured with time and like, I want to make sure I get through things, focus on section 20, 21. Those are the biggest parts of the project. But then when you get to section 23, there's all very important stuff. But the MLE section in particular is very math heavy. It's a kind of convoluted, kind of hard stuff to wrap your head around. So I want to walk you guys through that process rather than, you know, have you guys read it and just be like, I understood each part, but I don't understand the whole total thing and what just happened. That's the feeling I usually get from students who've gotten to that section. So I'm giving you guys a little heads up. But the rest of it, for example, like Bayesian classification, and then later on section 24, resampling and Monte Carlo, those are really useful parts. You may or may not use them in the project, depending on, you know, your preference. You probably use most of the stuff from 2021 and then maybe 22. Okay, cool. Sound good to you guys? All right, so I'm gonna go ahead and start sharing my screen. Let's see here. And as always, this should, well, actually right now, so usually as always, these notebooks would be on the GitHub repo that I share out. If you have forked it at some point or cloned it at some point, you might want to do a Git pull because there's some updates and stuff that I've kind of changed in there. This is one that I haven't uploaded to GitHub yet, so just know that try searching for this right after this section. You're not going to find it. I'll make sure to let you guys know when this section is available. So the main thing we're going to talk about is going to be basically Bayes theorem, which is kind of, I don't know, some people kind of have a little bit of a cult following sometimes for Bayes. And maybe it's deserved, maybe it's not, but Bayes is a pretty cool person. So let's get right into it, right? So Thomas Bayes, like I said, the badass of probability. This is literally like, I searched, like, I'm like, oh, I wonder if there's any interesting pictures for Bayes badass. And this is the first thing that popped up. And basically know that, again, there's a lot of people who have a lot of connection with Bayes in the sense that, like, he was a really great mathematician, lived in about the 1700s. He basically, his most famous theorem, which we'll talk about, Bayes theorem, actually was kind of like, he kind of was like, oh, this is so obvious. I don't even have to write this stuff down. So he kind of comes up with this idea. So it's kind of a cool thing to think about. But basically just know that Thomas Bayes comes up with this stuff and he thinks of this way of thinking of probability, which I think is actually, in my opinion, is actually a really natural way of thinking of probability. So so let's see what, like, these Bayesians, people who follow Bayes, like, what do they say? So I kind of make a joke here. Basically, C-3PO is wrong and Han Solo is a badass. So this might not make sense a whole lot, but is anyone here a fan of Star Wars? Well, first of all, has everyone seen Star Wars? Like, I'm assuming most people have. No one's not seen Star Wars, right? Okay, I see. It's okay. Like, but you were like, by pop culture, like, diffusion, you are familiar with the idea of Star Wars, right, Tara? Okay, cool. So you don't have to be like a super fan or anything like that. For the record, I am not like it might sometimes, like, you might think I'm a super nerd and stuff like that. I really don't know a whole lot of, like, nerd stuff. I'm familiar with it by, funny enough, association. But I want to say one thing about, is anyone here like a really big, like, and I say in a good way, a really big fan of Star Wars? Okay, good. So if I say like extended universe, no one knows what I'm talking about. Okay, exactly, right? So I'm not this person, but I'm fairly familiar with, like, some of the names. And I found out, like, one of my, when my wife was teaching, like, a first grader and their parents, big super nerds. And this is completely off topic, but I feel like I want to share this because it's so ridiculous. But their kid's name is Mara. And I was like, oh, that's a nice name. Like, you don't hear Mara too often, like, you know, some places. And it's like, oh, her full name is Mara Jade, you know, Mara Jade, like, that's her first name. And I was like, wait a second, Mara Jade, Mara Jade. And I was like, why does that sound familiar? And I realized at some point, I was like, oh, that's in the extended universe of Star Wars is Luke Skywalker's wife. And I was like, oh my gosh, I didn't know someone could reach that amount of like, just like nerd credit of this, like naming your firstborn daughter after Luke Skywalker's wife in the extended universe. Like, I'm just like, anyway. So anyway, Star Wars. So this is a great article that talks about Bayesian statistics based on Han Solo and C-3PO, like literally one scene. So if you've watched the original, I think it's Empire Strikes Back, yeah. So what's that? I think that's the second movie. So in the second movie, Han Solo is supposed to be like, you know, a really great pilot and everything like that. And C-3PO, his robot, basically, or not his robot, but it's a robot that says like, oh, the odds of like, you know, sir, the probability of successfully navigating an asteroid field is approximately 3,720 to 1. And he kind of says this famous line, never tell me the odds to C-3PO. And so this person, obviously a fan of Star Wars, goes in to say like why this is actually a big deal. And so it's kind of a cool way. I would strongly suggest like reading this through. Even if you're not a big fan of Star Wars, it makes a lot of sense. Basically, they go through saying, well, we kind of come in with this, C-3PO has this idea. It's like, well, okay, like so many people have, you know, gone through these asteroid fields and many have not survived. So our probability of actually surviving is very, very small because that's the number of people that they go through. So he kind of does the quick numbers on here. And I think he ends up saying like 2 out of, has recorded 2 people survived, instead of just making up numbers, 2 people survived out of 7,440. That's where his number comes from, C-3PO. And so he's like, okay, like that's what he thinks. And he says, okay, this is C-3PO's probability density function, right? Or his PDF going on here. So you can see it's like, okay, like this is little probability. So you see most people do not succeed, right? Most people do not, you know, basically fail. And so this is where this probability density function comes in. And so he's like, okay, this is why C-3PO says like, you're probably going to die. Like, let's not do this. And the thing is that Han Solo is a really great pilot. And because Han Solo is a really great pilot, this assumption is actually not quite right. Basically, we have the knowledge that Han Solo is a good pilot. He's actually going to do a really good job flying through this asteroid field, better than most pilots. So his expected like survival rate, like if you said like multiple Han Solos and send them through, it's going to be higher than this very low survival rate of what C-3PO has recorded before. So this kind of article kind of walks through here and saying like what this kind of looks like. Really easy read. It's not too much mathematics too. And basically he talks about like, let's say his distribution, it doesn't really matter. Basically his like his probability density function, and says, okay, well, what happens, like we really want to find out what is the likelihood of Han Solo actually surviving. So this is where we basically have something called our prior, so kind of like our prior knowledge. And our prior knowledge is that Han Solo, quote from the article, is a badass. And so since Han Solo is so good at piloting, you know, he has a higher probability of actually surviving, versus the likelihood, where the likelihood is really what C-3PO is saying, like, well, this is how many people have actually survived going through this asteroid field. So it's very, very unlikely. And so by having these 2 parts balance out, we have something called the posterior. And this posterior is basically saying how, what's it called? How likely Han Solo, not just any pilot, but Han Solo will actually survive this asteroid field, given that this asteroid field is very, very deadly to most pilots. So this is kind of like what it goes through. And basically they kind of give some numbers. It's kind of fun that they kind of end up doing this. And he ends up finding this, oh, there's a 75% chance of him actually surviving, which the author kind of reasons like, that's actually a pretty good reason. Like we know Han Solo is probably not going to die in this, but, you know, it gives us a little bit of, you know, oh, it's pretty dangerous. You know, maybe he won't survive. So it's a good article. I would suggest reading it through, especially after going through Bayes Theorem, when we're going to talk about today. I think it gives a good solidification of like what Bayes Theorem actually kind of like is saying. Okay. So anyway, cool stuff. So Star Wars. Okay. And so basically Bayes basically says the interpretation of a probability. So this is the Bayesian interpretation of probability, the expected outcome based on some prior knowledge or belief. So this is kind of a little like, this is kind of what intuitively say. So like we say like, oh, what's the probability of Han Solo surviving? And we kind of say like, that's our prior knowledge. Like, well, we know Han Solo is a very good pilot. So we say there is a certain percent of him actually surviving. Note that that's not based on experiment. That's basically based on our belief in that system and saying, okay, this is what it's going to be. And it's based around our prior knowledge. And so I keep highlighting this prior part in here, and we'll see this again. That's kind of like something that in a lot of ways we kind of either assume or just literally like guess. Sometimes our prior knowledge might be a very, very low number when in fact it should be a high number. But a Bayesian would really basically, or Bayes, I think it's Bayesian. So if you were a Bayesian, basically you would update your beliefs based on things that you see, and you say, oh, well, I had a prior knowledge of low probability, but I will change it basically into my posterior to say updating my belief. So for example, if you believe that, let's say it's always sunny every single day, because all of your days that you've ever lived have been sunny, right? Well, when you have a cloudy day, you have to update your beliefs. Like, well, okay, maybe it's mostly sunny, but sometimes we have clouds. And then if you see more and more clouds, like, oh, turns out, after being alive for 300 days, you're like, oh, turns out it's about even. Maybe it's sometimes sunny, sometimes it's not. So you would keep updating your beliefs versus, basically just testing everything out and not saying at the very end what that probability is. So it's a little subtle differently. So some other non-Star Wars examples of this kind of going. So every time I flip a coin, this coin, it landed on heads. So next time I flip it, it's likely to land on heads again. So clearly this one's much more like, depends like, what do you mean every time? Because if you flipped it 10 times, right? Maybe you did get heads, maybe you just got lucky. But if you flipped it like 100 times and you got like heads every single time, you'd probably feel like your prior knowledge based on those 100 flips, it probably means that coin will land on heads the next time you flip it, right? So this is kind of like the idea of Bayesian, like using your prior knowledge. Again, like the Star Wars, I guess I lied, there's another Star Wars, but Hans is one great pilot, so he likely will get through the asteroid field, even if others fail, crash and blow up. So basically it's like, oh, based on our prior knowledge of something that we know, or at least we believe that we know, we can use that to update what we think the situation will come up for the future, okay? So hopefully that kind of makes a little sense. As thumbs up if that making sense, like how we use our prior knowledge to get to stuff, cool. And later on, we'll talk about MLE, like not today, but like I said, but later on we'll talk about MLE, and that's gonna be very similar to what we're talking about with Bayesian, okay? So, oh yeah, go ahead. I see a question.
Yeah, so with the coin flip example, we're talking about the specific coin and not our knowledge of coins being flipped, right?
Right, it would be like
the
saying that
difference.
specific coin. You could technically bring it up to say, oh, I know coins in general flip 50-50, so this particular coin that's nothing special will likely have that same property. You could do it that way too. It doesn't necessarily have to, but in this scenario, like, yeah, I'm talking about this one specific coin. And note that this could also go the other way. If I flip the coin and I find that it goes 50-50, then I know that there's a 50% chance that it'll land on heads. And that's based on my prior knowledge, okay? So this is the other faction, the frequentists, and this is where like, a little Star Wars reference, right? But basically another kind of like way of thinking things. And the curriculum talks about Bayesian versus frequentists, and so I'm kind of bring this up, and this comes to classic. And it's subtle, it sounds very similar, but it's a little different. So a frequentist interpretation of probability, it's the limit of the frequency after many, many trials. So basically what happens is that when you do many trials, a large number of trials, you would basically, you start off with no probability whatsoever. You're like, I don't know what's gonna happen. And you try 1,000 times flipping this coin. And after 1,000 flips, then you decide, oh, it's going to, like, based on that 1,000 flips, you're like, oh, I'm approaching this number, which is like 50%. This is a little different from what we talk about as a Bayesian. A Bayesian says you basically start off with some prior idea, and that could be based on evidence, or it could just be like as a guess. It's like, well, I think most coins will land on 50-50. Like that's kind of like what our prior is starting with. But then what happens is that we update that belief as we go over and over and over. Say, oh, we were closer to 50% or we're further away from 50%. So there's kind of like a little subtlety difference, if that makes sense. One is the frequentist basically says probability is only defined by once we do it many, many times and we approach that. Bayesian interpretation of probability is that we can start off with a probability, but we can ultimately keep adjusting it as we gain more and more evidence, okay? And so, like I said, like assigns a probability to a hypothesis, and then frequentists basically test the hypothesis and determine probability with repeated trials. And there's not really a thing of like saying you are just a Bayesian versus just a frequentist. Sometimes you're a frequentist, sometimes you're a Bayesian, right? It just depends on the situation. So kind of quick, like, check-ins, like, all right, does this make sense? When would it make sense to think like a Bayesian versus a frequentist based on what you know? So like, can anyone think of an idea like when either it makes sense to think more Bayesian or more frequentist? Okay, so let me ask you guys, can someone just kind of reword this? I'll give you an example, okay? So if we don't have any knowledge on coins at all, right? Would it make sense for us to start off with an initial probability for that flipped coin? Probably not, right? So in that case, you, in a lot of ways, probably would start off as a frequentist. Like, let me try it out a few times and see what that looks like. And then once we try it a few times, maybe only 10 times, we have some idea. Maybe you get like 60%. You're like, oh, coins must land 60% on heads. Maybe that's just my first initial, exposure to this. And then from that point, you might be able to use that Bayesian knowledge and keep updating it. Usually, for example, we wouldn't want to like flip, let's say, like you wouldn't want to flip a coin 1 million times just to see if it's 50-50. Like you probably have an idea that it's probably 50-50 to begin with. You don't need to go to a whole bunch of things just because like we're like, oh, we want to start off this very beginning. You probably would start off with the Bayesian, like, well, it's probably 50-50. And then if you test it, I was like, oh, you might have to adjust your probability, your prior, like you take your prior and adjust your posterior and say, oh, now that I flipped it a bunch of times, I can see that it's not quite 50-50. So still going off of that 50-50 will be easier. There's also a subtlety to this. It's called the Bayesian Trap. If you set your prior knowledge to basically saying heads will never land, on a coin, you start off with a very, very small probability. And basically it'd take a lot of trials to basically convince someone to say that you were out of this, to the point where basically in a lot of ways, since you have such a huge prior knowledge where it's like, oh, like you kind of reject all like mathematically like reject all evidence. Another part of this is like, never setting anything to 100%. So for example, it's like, well, maybe the coin can, I'm trying to think of a good example of this, but like, let's say I look outside, like, oh, the sky will be purple. And it's like, well, that will never happen. But like as a Bayesian, you're like, well, it can never be 100%. So I'm gonna set it like 0.999%. And technically, because it can always be purple, like there's always that in mind, even though like, it probably doesn't make sense to have it purple too. So like, there's a few reasons like why you might want to like make sure your like prior knowledge isn't set too extremely, because otherwise it would take a lot of time to adjust this part. And so this is more like a philosophy part. So there's not like a right answer in this, like when it would make more sense, but just know that sometimes it makes more sense to be frequentist, sometimes it makes sense to be Bayesian. Okay, so this leads us all into Bayes' theorem. This famous equation that, fun fact, Bayes never wrote down this theorem. He never wrote down the equation. You will see it everywhere. In fact, he never even published it. He never published the idea. He actually thought it was too obvious. He was kind of like, and I'm saying that until like, oh, he thought it was so obvious. It's just more like he didn't think it was like revolutionary. He's like, well, duh, you just update your belief based on what you have prior knowledge on. And so it's funny is that he actually, when he passed away, his family actually asked Richard Price, another mathematician, said, can you go through his stuff and just see if you can find anything that's interesting? And he actually came across this concept of basically what became to Bayes' theorem. And basically that was the thing. It's like, oh, wow, this is actually a really like cool idea of updating your knowledge kind of deal. And that's where it started off. Again, fun fact, the Bayesian equation, or Bayes' theorem, sorry, that's my dog in the background, being a little nuisance anyway, but we have like our Bayes theorem. That Bayes theorem actually was written by another mathematician called Laplace. And if you know Laplacians, for example, that's the same mathematician. So know that Bayes theorem doesn't actually, Bayes never wrote it, but the concepts of Bayes theorem actually does exist from Bayes. So that's why we call it that. Okay, so I'm going to talk about this very classic experiment, thought experiment. And there's this quick video right here that I kind of linked off to from Matt, his name is Matt Parker. I don't know if anyone's familiar with this. Probably not, because you guys probably don't watch a bunch of educational YouTube videos about a bunch of mathematics, but he has some great videos about mathematics, and they actually go to Bayes' house and talks about like, this demonstration of this experiment. But basically, Bayes had this idea of this thought experiment of you sit behind a table. So like you imagine there's a table behind me. And what you do, you essentially toss just a ball, and the idea is that you randomly throw the ball and it lands behind on the table, somewhere on that square table. And then basically you say, okay, cool, like that's where the ball is. And then you throw another ball, like let's say you had a blue ball, you throw a red ball. You throw this red ball and it lands on the table. Then you tell your assistant, say, all right, where is the red ball in relation to the blue ball? And you say, oh, it's, a little further up, a little further north. For example, in this video, it talks about north, a little further north, a little bit east of it. And so he's like, okay, that you know generally where the relative position is, but you don't know exactly where it is. So you basically throw another ball, hopefully randomly, on this table. And as you throw more balls, you know, and hopefully it's actually random as you're throwing it up, you would get a better and better picture of where your original first ball actually landed on that table. And so this is the idea of like, you don't know actually to begin with, and you kind of keep updating your knowledge over and over and over again. And this is what the thought experiment that Bayes had. And this eventually got formalized as Bayes' theorem. Okay. Any questions on like what I mean by like this kind of experiment? I think you kind of picture this, right? It's not, again, a lot of Bayes stuff doesn't seem super complicated. At least I hope it doesn't sound complicated. But you can kind of see how you can like adjust and like figure out, for example, if your original ball landed like in the top corner, and every ball that you throw out there is always like to the, basically it's like, oh, it's really far down, or it's down into the left, then you know it's going to be to the top to the right, because almost no ball basically landed next to it kind of deal. It's like, oh, that means it must be in that corner. And that would only be true as you throw many, many secondary balls. Okay, cool. So this is when we get to actually see some math. Yay, math. All right. So you can say I had a very emoji day today when I was kind of putting this together. But so anyway, so math time. So this is when we actually get to see Bayes' theorem. So there it is, and it's all its glory. Oh, well, that's really messy. Okay, there it is with partial its glory. Okay, so this is usually how Bayes' theorem is written as. And so remember kind of going back to how probability is written out. We say this, for example, capital P represents probability of. So this can be read as like this PA, you know, line B. This can be read as like the probability of A such that B, or the probability of A given B. So the idea here is that what's the probability of A happening such that B already happened? So you can kind of think about this, for example, the probability of being cloudy and the probability of like, you know, lightning. And it's like, what's the probability of it being cloudy such that we know there's lightning? And you could probably guess, oh, that's 100%, right? Like, I mean, near 100%. I don't think there's many times there's like, I don't know, I'm not a meteorologist, but I'm assuming most of the time there's clouds when there's lightning, right? And so they know that's different from saying the probability of lightning, which is like it would be given A, the probability of lightning given that there are clouds. So note that just because there is lightning, there are clouds every time there's lightning, it doesn't necessarily mean that because they're clouds, there will be lightning as well. Does that make sense? Kind of the inverse. And that's what this B, that line A. So you'll hear that as B given that A, or B such that A. So kind of mathematical lingo. I kind of want to remind you guys. I know you guys have seen this before, but I wanted to make sure you guys remember this. So again, this is the glory of Bayes' theorem right here. And it's actually a pretty small equation, right? It's just four different probabilities. A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Pretty straightforward, right? So you give these different parts, and you actually look back on like Han Solo, you'll see here, he kind of uses this part. I like the way he phrased this. It's the posterior is equal to the likelihood times the prior, and our prior is our prior knowledge. So you can see here our PA, and I kind of separated this out just to make it more obvious. This PA is our prior knowledge, okay? Sorry, my dog's getting into something. But our PA is our prior knowledge. So it's something that we already like know. So it's something like how badass is Han Solo, or, you know, how likely is our coin flip, you know, from our prior knowledge. Oh, it's a 50-50 chance. So P of heads would be 50, like, or 0.5. PAB, or so PA, so probability of A given B is our posterior. That's what we want to know. We want to say, what is the probability, you know, of actually doing this? So, for example, going back to our Han Solo scenario, it's like, what's the probability of Han Solo surviving given that so many people died in the asteroid field? Okay, and then our likelihood, and depending on who you talk to, you know, how you would phrase this. I kind of think of this as together, kind of normalized, but basically it's the probability of B happening such that A happens, and then it's normalized by dividing by the probability of B. So basically what's happening here is like, how likely is B going to happen such that A happens, divided by all the times B happens. And that gives us our likelihood. And this is kind of like when we'll talk about, like, for example, you'll sometimes see this coded as like likelihood odds and stuff like that. This is where, like, for example, the odds of, you know, you passing through the asteroid field is like 3,143 or something like that, right? So that's like the odds going on here. This is kind of what this is being said, okay? So basically this Bayes theorem is coming into three parts: the prior, what you already know or what you assume is true; the posterior, what you want to know, basically your updated belief; and your likelihood, basically on like some probability of, you know, what the situation is based on other parts. So this is kind of how we can put these parts together. And so this is going to go into our example of like really classic of like if you tested positive for a disease. But before I get into that, does anyone have any questions on these three different parts, what they represent, and how they form Bayes' theorem?
Sorry, how exactly would you phrase the likelihood division using the Han Solo example?
Yeah, so like when, good question, Nicole. So when, was it C3PO says, I'm trying to look for the number, when he says 3,720 to 1, that's what this is. It's our 3,721 to 1 kind of deal. Or I guess opposite. Like basically that's the likelihood odds. So sometimes you'll see people phrase it as odds, and that's basically when you see 3,720 to 1, that is an odds. That sounds really confusing the way I phrase that, but that's kind of like what the phrasing would be. That kind of makes sense? Okay, cool. So this kind of goes into, let's work some examples, right? So pretend we test positive for a disease, for a rare disease, not just any disease, but a very rare disease. So you can say like, all right, we test positive for a disease. You're like, oh shoot, like, you know, like we have this super rare disease. We're probably gonna get sick. We're gonna have to take, you know, these placebos forever. We're gonna be a hypochondriac forever, right? That's this rare disease, the hypochondria. You're not really familiar with doctors, like, but anyway, so like if you have some rare disease and you test positive for it, you're like, oh shoot, you know, like how worried should I be? And they say to you, okay, like you tested positive, but we're gonna do a secondary test that's completely different from the first one to confirm if you do have the disease or not, right? And you go home and you're like, oh shoot, like I had this disease, it's so scary. So then you start thinking about this math. You're like, well, okay, how likely am I actually gonna have this super rare disease? And we can actually use Bayes' theorem to figure this part out, amazingly enough, or at least get an idea, right? So let's give it some setup. So I said it's a rare disease. I'm gonna say a rare disease being like 0.01% of the population, which actually isn't super rare, I guess. Like that's not a huge amount. Like you think of like 1 million people, that's still quite a lot of people who would have this disease. But basically 1 out of, what's that, 10,000 people would have this disease. So relatively rare, right? And we're gonna assume the test is 99% accurate. Note that I'm gonna say 99% accurate, meaning that if it correctly identifies 99% of the time whether you're sick or not. So if you're sick, 99% of the time it identifies you as being sick. And if you're not sick, 99% of the time it'll correctly say you're not sick, okay? Note that those numbers don't have to be equal. I'm just making it easy so we don't have to like worry about that. And you can also still use that with Bayes' theorem, which is kind of good. So my question is, like, what does this formula look like? So how would we kind of formulate this one into here? And so I want you to think about it a second, just like think like, all right, this probability A, probability B, like what are the different parts I would fill in for what I'm trying to look for, okay? And so, go ahead. You want to say something, Giovanna?
No, I was just gonna say the probability of A would be the 0.01, right?
Yeah, so probability of A would be like, you know, let's say if the probability of being having a disease, right? And that would be our prior, saying, okay, that would be like very, very small, right?
Okay.
What we really want to know is a probability of A given B, like what's the probability of me actually being sick given I tested positive, okay? And that's how we want to phrase it, right? So let's kind of check this out, right? So I kind of wrote this part in here, and I didn't expect you guys to like come up with the formula automatically. Like this definitely takes a little bit of time to figure it out. But I think an easy one to figure out first is say, what do we want to find out? We want to find out what's the probability of me actually being sick, A, given that I tested positive, okay? Or I'm sorry, yeah, no, that's right. So we now want to say, okay, we use Bayes' theorem. So basically we say the probability of being sick such that we're given that we tested positive. I kind of swapped this over with this A part. Let me close this up, there we go. So we can see the probability of A is the probability of being sick times the probability of being sick given that, I'm sorry, probability of testing positive given that you are sick, right? So we should hopefully know what this value is. Hey, stop it. Sorry. So we actually know this number. We say, okay, well, if you're positive and you're sick, right? What is this probability? And we also say the probability of being actually having positive. Sorry, guys. She's so needy. I know. Okay, thank you. Now go play. Not too hard. Okay. Sorry, everyone. All right, stop. I know. I'll give you guys a few extra minutes. Delta just wants to say hey. You can see her stinking cone. You think she would be more embarrassed, but she's not. She's like, whatever. All right. So the main thing is that that's our Bayes theorem right there. Now you want to jump off. Okay. All right. So this is the main part. We want to see what's the probability of being sick such that we are tested positive. Okay. So we can simplify it by knowing the probability of testing positive for each case. So right here, we can say, what's the probability of being tested positive, right? And note that that's not simply just like saying 99%, right? Because it could be like we could test positive even though we're not sick, right? Which happens 1% of the time, 1% of the time, even though we're like healthy, right? So we can actually simplify this by saying, okay, oh, this is kind of, sorry, everyone, make sure this, can you see that okay? You guys see that too, right? There we go. Okay, sorry, I got scooted off to the side, so I want to make this. So the probability of being positive is going to be equal to what's the probability of being sick times probability of being positive, saying positive, and you are sick, right? So obviously we need those parts. So this right here, what would this probability be right here? The probability of positivity such that we're sick. Anyone got a guess? So let me ask you guys, if you are sick and your test says, like, you know you're sick and you test positive, what's the likelihood of you actually being tested positive, it correctly identifying that you are in fact sick?
The 99%?
99%, cool. So yeah, this is gonna be 99% here. And what's the probability of us being sick?
0.01%.
0.01%, good. So that probability of being sick is very, very small, but it's going to be, of all those people who are who are sick, even though it's a small population, 99% of them are going to be correctly identified as positive. Now the opposite happens, like the probability of us not being sick, okay? What's that probability of us not being sick in this scenario?
99%.
99%, right? So which is 1 minus our 99, or I'm sorry, I guess it's smaller than 99%, right? Or bigger than 99%. So it's 1 minus 0.01%. So
yeah, 99.99.
Yeah, so that's right, yeah. So I think that's what you're doing. I'm gonna assume that was right and I misspoke. So, but yeah, so that's gonna be, most of the people are not gonna be sick, but the probability of being positive, basically being incorrectly identified by the test as being sick, is going to be very, very small. Basically 1 minus 99%, or 100% minus 99. So this right here would be just 1%, right? Okay, so let me get this part. Let me get, oh my guys, go, sorry. So we can basically take this probability, put it on the very bottom here, and we get this very long equation, but basically it's the same equivalent as this going on right here, okay? So with this guy, we can go ahead and work it out further, because we can basically say, oh, we know the probability of being sick, we know the probability of being positive such that you're sick, correctly identified as being sick, and then we basically know these parts basically say it again, and we know this part right here because we know basically if you're not sick, you just basically 1 minus, you know, the probability of actually being sick, and then the probability of it basically the test getting wrong. So we know that's 1%. So we can actually work this out in code. So we define the probabilities, okay? So the probability of being sick is, I put into decimal form instead of percent, is 0.001, and so the probability of not being sick is going to be 1 minus p sick, which Thomas said was going to be 99.99%, okay? And then say, okay, the probability of test being correct, so accurate, right? So the probability of being sick, probability of testing positive such that you're sick is going to be 99%. The probability of testing positive but you're not sick it's going to be 1 minus the probability of positive such that sick, right? So you can see this notation like very verbose, but like also still hard to say. Okay, and then you can see our last part is going to be the probability of being positive. Hey, sorry, everyone. I don't know if you can hear. Can you guys hear that? Okay, so they're just playing and everything like that. So the probability of testing positive is going to be those combined probabilities right here. And so we could basically just add those parts together since we already have this defined, right? So cool. That was pretty easy, right? The next part is just defining the parts for Bayes theorem. So I actually wrote a little function here. So first I had a prior. So to make this, hey, stop it. So our probability of, the prior is going to be the probability of being sick. So that's our P sick, right? Our likelihood is going to be our probability positive such that you're sick divided by the probability of being positive, okay? And so just combine this together. So that's going to be our likelihood. And then I made a nice little function called find the posterior. Sounds like a great game, right? So you find the posterior. Okay, so anyway, we find the posterior here, prior basically times the likelihood, basically coming from this Bayes theorem here. And then we can get the final result, say, all right, probability that you're sick equals find the probability, prior times likelihood. You have a blank chance of actual being sick. Oh no, someone left. I hope they get to, I don't know if someone left. We're about to big review. So any guesses like how likely we're going to be sick that we tested positive for this rare disease? Random guesses. I'm trying to build like a little suspense. No, you guys are all wrong. No, it's 9%, or not even 9%, less than 1%. So even though the test is 99% accurate, and we tested positive for this disease, we still only have like a 1% chance of actually having the disease. So let me ask you guys, does that make sense? So I see some faces, like a couple of like, I don't know, Victor. Like that doesn't seem quite right, right? So I kind of left this little blank here to kind of make you guys sweat a little bit and be like, I don't know if that makes sense. And I will tell you that I would say, yes, that does make sense. And the reason why is not because I came up with the answer and I want to cover my, cover my butt, basically, oh, it's right. But really what happens, like if this disease is very, very, very rare, most people who are going to get the test are not going to be sick. So the problem is that you're going to have a lot more false positives in this case. And so you would expect, because the disease is so rare, only 1 in 10,000 people actually have the disease, that most people who actually get the test and test positive are probably going, and this is assuming it's random, right? It's not like, oh, you're already like throwing up because you have the sickness. It's like, oh, you're just randomly testing it. Is that most people won't have, most people are just going to be not sick and they're going to test positive. So, okay, so hopefully that kind of makes sense a little bit, like why it's so small. And this actually kind of should help you feel reassured too if you ever go into a test that's actually kind of like a rare disease. Just as you test positive doesn't necessarily mean you are in fact positive. So what do they usually do if you test positive for a test and they're like, I don't know if anyone's ever been in this situation. Hopefully you haven't been, in the sense that it's a lot of drama and stuff like that. But usually what you do if you test positive for one test, for example, has anyone got like a TB test before? So tuberculosis test. Okay, so if you're a teacher, at least in California, you have to get tested every 2 years to see if you have tuberculosis. And so most people, like if you don't have tuberculosis, they basically say, okay, you don't have tuberculosis, you're all good. If you test positive for tuberculosis, it doesn't necessarily mean you actually have tuberculosis. So they actually do a secondary test with like an X-ray. So the first one is they shoot like a little I don't even know what it is, I'm not a medical person, but they basically give like some kind of thing that will react if you have tuberculosis, this little bubble, and they come back in like a few days and you're like, oh, you still have a bubble, you might have tuberculosis. We have to do an X-ray scan of your chest to see if you actually have tuberculosis. And so the idea here is that you would take a secondary test. So we can kind of pretend, what if we test for a disease twice? So assuming that the tests are independent from each other, so they're not related to each other, because obviously if the test is like related every single time, you might continuously test positive even though you don't have the disease. So how would we do this? So let me ask you guys, is anything changed, like of all this process that we did going through here, the probability and stuff like that, what part would change? And I'll give you a hint, there's only one part that will actually change in this setup. All the way to part. Okay. So it's either going to be the prior, the posterior, or the likelihood. If we tested positive for a disease once, and we're going to get a secondary test, there's only one of these things that would be changed. And does anyone have an idea what that change would be? All right, we'll do a little vote then, okay? So we're gonna have prior is gonna be number 1, posterior is 2. Oh, sorry, did someone
The prior is going to change.
The prior is gonna change, good, all right. You saved everyone the voting sequence. Thank you, Phyllis. So yeah, so the prior is gonna change because we now know the prior is different. We now have new knowledge going forward. The posterior is what we're trying to find. The likelihood hasn't changed basically, right? There's still the odds of, how frequently the disease occurs in the population and such, right? So that hasn't really changed. The real big part is the prior. And so we actually can write this in the code now. Say, okay, all we gotta do is say the prior is the probability of you're sick, right? And let's see here, I go ahead and run this now. So this probability is gonna be the posterior from the previous one, right? So there's only a 0.98% chance that you actually are sick, right? So we now know how that new information, and now we take the same test with the same 99% accuracy, right? So if I do this now, again, the only thing that's changed is the prior. I run this. Anyone got a chance? Any guesses on what the probability is going to be? Is it going to be higher or lower, you think?
Higher.
Higher, right? Because if you test positive twice on a test, you're more likely to have the disease. Is it going to be significantly higher? Because remember, the first time you had only 1%. Or do we think you're going to be like a little bit higher? Are we going to be like really high? Like, what do you guys think?
I think it should be just 0.09 or something.
Like a little bit higher, right?
Yeah.
You had 2 tests. Like the first test, like, oh, super rare, right? So it's probably not going to be that common. Yeah, any other guesses? Okay, Phyllis for the win for contributing. So you get a gold star, all right? But it turns out it's actually a very high chance. So it's a 96% chance. And hopefully this actually makes intuitive sense of like what you'd expect in the real world. If you took a test and got positive, even though it's unlikely for you to actually be, actually sick, if you get test twice positive, right? If you're positive both times, then it's a much higher chance that you are in fact sick. And that's what we'd want, right? We want a secondary test to basically confirm, are you sick? And the real reason why it's changed is because of that prior knowledge that we went from, instead of the probability of you being sick of 0.0001 is now 0.1%, or just, I guess, 0.001, right? So we moved up like 2 decimal places. Now we actually have a higher chance of being sick. And this is when we actually see, we actually have a high chance of being sick now that we tested positive twice. And this is the idea of the Bayesian, like being a Bayesian, is that you update the belief as you kind of go through it over and over and over again. Okay. Does everyone understand kind of how that looks? Cool. All right, any questions on this prior posterior likelihood? Okay, not too scary, right? Like, I know there's a lot of like little math going through here, but the main thing is basically think like, all right, you have some prior knowledge, this prior PA, your posterior, basically what you're trying to figure out, and then the likelihood. Basically, this is based on like some knowledge of like, the world and how it like structured. So sometimes we don't actually, like the hardest part of this, does anyone got to guess, like besides the posterior, obviously trying to get it, does anyone got to guess like what would be the hardest part to actually figure out? It's probably the prior, right? But you don't necessarily know if it's true or not. Like that's kind of like the prior knowledge you have to come up with. And note that you can start off with a wrong prior, but then keep updating. But if your prior is so small, for example, like I said, the probability of A, if it's like 0, right? What happens to your posterior if PA is 0? Going off of this equation right here.
Could be 0 too.
Maybe 0 too. Yeah. So fun. I think I mentioned this before. I had a professor who told us when he was like back in like physics, there was always the 0 or 1 guy. And so whenever the professor would say, like, oh, what is his value? That guy would always yell 0 or 1, basically because like usually it's one of those 2 things. So yeah, it's 0 in this case. But yeah, because the probability of A, if you think you are you have no disease, there's no chance you have the disease, your probability of A is 0. So in this case, your posterior is like, well, there's no chance I have the disease, so I can't have the disease, even though I tested positive. And so this is where obviously you kind of get in this Bayesian trap. You're like, oh, like, well, you can have that disease, you know, because your probability was so low, and this fact 0, you'll never be able to update your, you know, beliefs, basically your quote unquote your belief, basically your posterior. Okay, and you'll hear this like say belief, but basically it's a technical term meaning your posterior. Okay, so I wanted to kind of add that in there. All right, cool. So this kind of hopefully gives you a little help with the curriculum going forward. I'm going to skip over MLE, which is kind of like in the middle of the section, and I'm going to talk about naive Bayes classification. To be quite honest, this is not going to be relevant to the project, naive Bayes classification. However, it's a really great introduction to machine learning going forward, because the classic example is talking about spam. So I'm going to go over a little bit, and I'm giving you that extra time because my dog kind of interrupted the show. So not really a show, but anyway, so we're going to go into Bayesian classifiers.